Welcome to our video on standard temperature and pressure. The learning objective for this video is partly to apply stoichiometric relationships to calculate amounts of substances involved in chemical reactions. So what is standard temperature and pressure? As we've seen so far in our gases chapter, gases have pressure, volume, temperature, and their volume is highly dependent on the pressure. If we have high pressure, then we'll have a smaller volume. If we have a larger temperature, then we'll have a larger volume. So there's a relationship between temperature and pressure. So if we're going to be reporting or measuring and comparing data sets, it's useful to have kind of standard pressures and temperatures in order to compare volumes of gases across multiple different data sets. So scientists just picked a pressure and picked a temperature and said, hey, we're going to call these the standard pressure and standard temperature, so that if you're doing an experiment and measuring things, if you could report your data in here, then we won't have to do a whole bunch of math when we're comparing our different data sets. And so for the most part, everyone's like, okay, cool. So our standard temperature and pressure in the United States, at least, is 1 atmosphere and 273.15 Kelvin, which is 0 degrees Celsius. So that's our standard temperature and pressure for gases. Now, if we do apply our ideal gas law used for 1 mole of gas at 1 atmosphere and 273.15 Kelvin, we find out that 1 mole of any gas occupies 22.4 liters at STP, and we can use that as a conversion factor in our math. You might have heard me mentioning that this is in the United States at least, and that's because NIST, the National Institute of Science and Technology, does use 1 atmosphere as the standard pressure, but the International Union of Pure and Applied Chemistry deviated from NIST back in 1982 in order to make this 1 bar of pressure, because 1 bar is more closely aligned to the SI unit for pascals. So 1 bar is equal to 1 times 10 to the 5th power pascals. And so they thought, hey, since pascals is the SI unit, we're going to say that our standard pressure is related to that SI unit. And the United States never switched. So we're still stuck with 1 atmosphere. The rest of the world uses this 1 bar. So just be careful when you are looking at internet resources, because you will find a mixture of both standards. So I mentioned on the last slide that if we do apply that ideal gas law to our 1 mole of gas at STP, our 1 atmosphere of pressure, we're going to solve for volume for 1 mole of gas. This is in atmospheres, so I'm going to use the R value that's in atmospheres to minimize how many unit conversions I need to do in my life. And then the standard temperature was 273.15. So if we calculate V here and type this all into calculator, we get 22.4 liters. So that means that 1 mole of any gas at STP occupies a volume of 22.4 liters. Think about that, like a 2-liter bottle of soda. This is about 11 2-liter bottles of soda, to kind of give you a size estimate. It's pretty big. So let's do a practice problem for your conceptual understanding. We have 3 balloons that all have equal volumes, and they're at the same temperature. And here we have masses of gases. So this first one contains 4 grams of helium. The second one contains 17.0 grams of NH3. And this third one contains 32.0 grams of O2. Which of these statements is true? Go ahead and pause the video and think about this. Once you have your answer, then unpause the video so we can compare. Okay, so all three balloons have equal pressure. That's because all of these contain equal moles. They all have 1 mole of gas. So even though they have different masses, they all contain the same amount. And so if we look at our PV is equal to nRT, or solve for P, they are equal volumes, so the denominator is the same throughout. They are at the same temperature, so that's equal, and N is equal. So all three of these balloons have constant, 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 constant. So pressure is constant throughout. Here is a second practice problem for you. This one says, assuming ideal behavior, which of these gas samples has the smallest volume at STP? Go ahead and pause the video and think about this. Unpause the video when you are ready to check your work. Okay, so since it says smallest volume, if we have the smallest amount of moles, we will have the smallest volume because these are directly proportional. So we're looking for something that's the smallest moles. The molar mass of H2 gas is 2.016 grams per mole. And this one is 32 grams per mole. And argon is 39.95 grams per mole. And so which of these has the smallest moles? So this is 0.46296 moles. That's pretty small. This is 0.03125 moles. That's even smaller. And then our last one is the smallest of all. So this one is going to have the smallest volume at STP because it has the smallest number of moles. We can also use this molar volume at STP as a conversion factor in our math. That way we can calculate the actual volume at STP. So this example problem reads, what volume will 5.50 grams of oxygen occupy at STP? So when we write this out, we have oxygen. Oxygen, we have to remember, is a diatomic element. It's one of our diatomic 7. That'll help us get its molar mass correct. And so oxygen's molar mass is 15.99999 times 2, which is 31.998 grams. You need to cancel out my grams, so that's in the denominator. And then I put the moles in the numerator. And now I can use my molar volume because it is a gas. And so we have and cancel out our moles of O2. And then at STP, 1 mole of any gas will occupy 22.4 liters. So if we type this into our calculator, we can get our answer, which is 3.850. This is 3 sig figs, so I'm going to need 3 sig figs in my answer, and so that is, I'll report my answer as 3.850 grams of O2. Not grams, liters. Liters. Okay, here's our next practice problem for you. It says, what mass of iron will react with 5.50 liters of oxygen at STP? Go ahead and pause this video so that you can work this out. Unpause the video when you are ready to check your work. Okay, let's go over this. So we're going to have to do some stoichiometry because we're told an amount of this and we're asked to find mass of this. So we're asked to find grams of iron from liters of oxygen. So once we go from liters to moles, we're going to have to go from moles to moles of a different thing and then back out into grams. So we kind of have a solution map sketched out. So we're going to do 5.50 liters of O2. Then since it is a STP and it's a gas, then we can say that we can cancel out our liters of gas at STP in order to get into moles. 1 mole of any gas at STP occupies 22.4 liters. This is O2. Now we need to cancel out our moles of O2 and get into moles of iron. This is our molar ratio from our chemical equation, also known as the stoichiometric factor. That's a 3 coefficient in front of the oxygen and a 4 coefficient in front of the iron. Now we need to go from moles into grams. And so anytime we want to go from moles to grams or grams to moles, we have to use our molar mass of iron. 1 mole of iron has a mass of 55.85 grams. So now we can type that into our calculator. And just a second while I type that in. That is 18.284 grams of iron. Check my sig figs. This is 3 sig figs. So I'm going to need 1, 2, 3 sig figs, 18.3 grams of iron.